So this is the new event camera data set that our group has come out with. It's a collaboration amongst Costa, CJ Taylor, Vijay Kumar, and Annie Shea, along with Fernando Cladera, Claude Wang, and Anthony Basolco. So we wanted to motivate why another event camera data set a little bit. And so two of the big players in event camera data sets are MVSec and DSec, and we all know and love them. And we wanted to really address some of the core issues and also just update a little bit. So in MVSec, it's fairly old sensors is primarily what we're targeting. With DSec, it's primarily driving sequences, which is what makes it great. Really nice, smooth highway, and really nice streets that we're driven on, and that's absolutely wonderful. But like Philly, for example, does not have wonderful streets, for example. So, and one of the other components is that we really want to have an impact on the robotics community by addressing edge cases that are more and more being studied and addressed in these larger systems, like what Vijay Kumar's group really does. And so within that, in the event camera world, we wanted to address some more of the IMO issues, high bandwidth from newer generation sensors, and also high amounts of vibrations that we see in certain platforms. Does this work? Okay. We have internet. No, do we? It might be. Okay. So, okay. I'm going to give up on the video and just let Fernando go over the systems. I apologize.
Okay, so this is an overview of the system that we use. As you see, it's a very compact platform in which we are integrating all the sensors all together. And the interesting approach is that we are using the same hardware for the different platforms we're running on, so there is no need of major updates when changing between platforms. The system is composed of an Auster OS1 LiDAR. It's an automotive-grade LiDAR with 64 channels. The OVC, that is an in-house computer vision sensor that we developed in our lab with Open Robotics that has a stereo pair plus military-grade IMU, a high-quality IMU. And we have the two event cameras, high-resolution event cameras from Prophecy, and we also have RTK GPS. We use the same platform in three different, the same sensor stack in three different platforms: the Falcon 4 UAV, a car, and a Boston Dynamics Spots. And we have three environments: forest, indoor, and urban. So these are the platforms that I just mentioned. So you see that the sensor stack is the same one among all of them. Quick overview on the hardware part. We focus on having hardware synchronized signals between the different sensors, and the key for doing this is the OVC that can generate from the high resolution IMU pulses that we have can decimate trigger signals to the different sensors. With these trigger signals, we are feeding the grayscale cameras, the RGB cameras, the Auster, and also the event cameras. And it's important to know that all the processing of the events is done after the fact. So we're collecting raw data and we're processing that afterwards. And this is a key part of our platform, because something that we're observing with high resolution event cameras on highly textured environments is that the event count can go quite high, up to 200 mega events per second. And doing the processing of those events in real time is one of the challenges that we're showing with this data set. So we are collecting all the data and we're processing it after the fact. We did some improvements on how to collect such a huge amount of data. As I mentioned, we are recording raw data from the different sensors, and we are trying to not mess with the parameters of the event cameras. We're disabling the event rate controllers so that these systems do not affect the data we're getting from the event camera. Some statistics of the data set: around 130 files, some of 65 of them are useful recordings. We have a few bunch of calibrations, and these are the numbers we are talking about when we talk about high resolution event cameras in very highly textured environments.
So one of the challenges with creating a data set like this is just doing the event camera calibration itself. And so we found that approximate image reconstruction is sufficient for April tag grids. And this was work that was done by Bernd Frommer, who was a former postdoc within Costas's group. And this is the wonderful reconstruction library linked down here. And we follow a standard caliber pipeline after we do that reconstruction. For ground truth pose, we leverage faster LEO so that we can have the same quality of pose in GPS denied environments such as the forest, indoors, or even Philadelphia city center where you have large sky rises and you get multipathing of the GPS itself. And just qualitatively, we observe about a 1 meter drift for the longest sequence that we have, which is City Hall, that single loop. Let's see if this video chooses to work. But on the left, you can see the art museum, the map that we were able to generate from the Philadelphia Art Museum of Spot walking up the steps. And from ground truth odometry and a ground truth map, we're able to generate a ground truth depth for our static portions of the scene. Okay, continue. And one of the core things that we found out while we were working on generating the ground truth depth is with the higher resolutions, you often see through objects because the point clouds are sparse. It's a small detail that wasn't needed to be addressed in the original MVSEC just because the resolution was significantly lower. And so we actually dug a method out from a little while ago. Just doing the hidden point operator on the point cloud itself gives us only the points that are directly visible from the current viewpoint. And then for semantic classes, for the data set, we warp images using the calibrated camera geometries, and we get a class label for every image frame with intern image, and it matches the cityscape labels. And for where to grab the data, we have a QR code and we think easy to remember URL, m3ed.io.